Have you ever settled into your window seat on a flight, stared out at the clouds, and actually thought about the window you're looking through? It's one of those design choices that seems incredibly simple, almost like an afterthought. But that shape was born from a mystery that literally shook the world's confidence in the early jet age. In this explainer, we're undertaking a serious investigation into a completely everyday aviation feature, uncovering the dramatic history and the invisible physics that shaped it. So let's dive right in. Why do modern airplane windows have curved edges? If you look closely at passenger windows on today's pressurized airliners, you'll notice they are typically oval or rectangular with highly rounded corners. You will not find a single, sharp 90-degree square corner anywhere in the passenger cabin. And to understand why, we have to step back into the early 1950s. This simple choice of curved edges stems directly from a devastating early jet age mystery. You see, to understand the danger that early engineers unfortunately overlooked, we have to look at the invisible physics of the air itself. Modern airliners cruise miles above the Earth, right around 35,000 feet. At that altitude, the air is simply way too thin for us to breathe normally. So to keep everyone comfortable and safe, the cabin is pressurized, meaning the air pressure inside is much higher than the pressure outside. In the world's first jet airliner, the de Havilland Comet, this normal pressure difference was approximately 8.25 pounds per square inch, or PSI. This internal pressure effectively turned the thin metal fuselage of the aircraft into a giant pressure vessel. Now, this brings us to what's known as a pressurization cycle. Every single time an aircraft climbs and descends, it completes this living, breathing mechanical process. The metal skin of the fuselage physically expands just a little bit as the plane climbs, and the internal pressure pushes outward, and then it contracts again after landing. This repeated expansion and contraction is a totally normal part of flight. But back in the early 1950s, engineers were still trying to figure out exactly how thousands of these relentless pressure cycles would interact with the shape of an aircraft's metal structure over time. Our story really kicks off in May 1952, when the British-built de Havilland Comet 1 made history. It was the world's very first commercial jet airliner. It was beautifully streamlined, and it could fly at about 460 miles per hour at 35,000 feet. That was over 100 miles per hour faster than many propeller-driven planes of the era. It was a massive leap forward. Passengers absolutely loved the smooth, quiet flight, and importantly, they loved the large, stylishly squarish windows that gave them an unprecedented view. For a year, it was an extraordinary success. But then, the accidents began. The first major tragedy occurred in May 1953, when a comet crashed shortly after departing Calcutta, India. Now, we need to make a very careful distinction here. Investigators attributed that specific accident to structural failure caused by a severe thunderstorm, or potentially over-controlling by the pilot inside that storm. They did not attribute the Calcutta crash to window fatigue. The official cause was the weather. But as the calendar turned to 1954, a far more troubling and mysterious pattern began to emerge in clear skies. On January 10, 1954, a comet departing Rome suffered a sudden, catastrophic in-flight structural failure over the Mediterranean near the island of Elba. The aircraft was operating under completely routine flight conditions. What totally baffled investigators was the flight history of this plane. It had only completed approximately 1,290 pressurization cycles. And then, just months later in April 1954, an identical tragedy struck. Another comet suffered an in-flight breakup near Naples, Italy, also while climbing through completely routine weather. And this aircraft had completed even fewer flights, approximately 900 pressurization cycles. Both of these numbers, 1290 and 900, were shockingly far below what earlier factory tests suggested the fuselage could safely survive. So the entire Comet fleet was immediately grounded, and investigators launched one of the most extensive forensic engineering efforts in history. To solve the mystery behind these incredibly low cycle failures, investigators at Farnborough, England came up with a genuinely brilliant test. They took an entire, fully intact Comet fuselage and placed it inside a massive custom-built water tank. By filling the inside and outside of the plane with water and then pumping additional water into the cabin, they could safely simulate the pressurization cycles of flight. Because water is far less compressible than air, it allowed them to repeatedly stress the metal without causing a violent, explosive decompression when the metal finally gave way. The specific aircraft they placed in the water tank had already completed 1,230 pressurized flights while in actual service. Inside the tank, it underwent another 1,830 simulated pressure cycles. Finally, the test fuselage failed at exactly 3,060 total pressurization cycles. The metal literally split open. This controlled failure provided the exact, decisive clue the investigators so desperately needed to solve the mystery of the Elba and Naples crashes. The technical culprit hiding in the aircraft's design was a phenomenon known as stress concentration. In a pressurized fuselage, structural loads have to physically travel through the aircraft's metal skin. If you have a curved opening, those forces can move smoothly around the edges. It's kind of like water flowing easily around a smooth stone in a river. But sharp, squarish corners, they behave very differently. At a sharp 90-degree corner, the stress can't flow smoothly. It piles up and becomes intensely concentrated in a very small area. The mechanical sequence of fatigue that doomed the Comet unfolded in 3 distinct steps. Step 1, the stress concentrates intensely at those sharp, squarish corners. Step 2, every single time the aircraft pressurizes and depressurizes, that specific localized area experiences much higher loading than the rest of the metal, which rapidly wears it out. And step 3, microscopic fatigue cracks begin to form at the corner. With every single flight, those invisible cracks grow until the metal simply cannot hold the pressure anymore, resulting in a sudden rupture. When we compare all the forensic findings, a very clear pattern emerges. In the Farnborough water tank test, the fuselage failed at the corner of a squarish forward escape hatch Migno. Meanwhile, when investigators managed the incredibly difficult task of recovering the Elba wreckage from the seafloor, they traced the origin of the fatigue not to a passenger window, but to the area near the squarish ADF windows on the roof of the fuselage, which housed radio navigation equipment. The damaged metal there showed unmistakable evidence of fatigue. So let's clear something up, because it's absolutely crucial. It is a major misconception to claim that an ordinary passenger window caused every single Comet failure. The forward escape hatch and the roof-mounted ADF windows were the actual failure points in the water tank and Elba incidents, respectively. The catastrophic flaw wasn't one specific window. It was the systemic engineering geometry of the aircraft. The underlying problem was the presence of sharp, squarish corners anywhere in a repeatedly pressurized metal structure. But this brings us to the final, most perplexing piece of the puzzle. If squarish corners were inherently flawed, why in the world did de Havilland's original safety testing completely fail to predict the disastrously short lifespan of the production aircraft? Before the Comet ever carried a single passenger, a prototype fuselage underwent extensive testing and appeared to prove the design was perfectly safe. So how could the tests have been that wrong? The answer lies in a metallurgical process called cold working. During the initial safety trials, engineers subjected the prototype fuselage to extreme overpressurization tests just to prove its ultimate strength. They basically pushed it to double the normal operating pressure. But without realizing it, this heavy overloading accidentally altered the physical characteristics of the metal. It stretched and actually reinforced the metal right around those high-stress squarish corners. When you look at the data, the contrast is stark and honestly tragic. Because of that accidental cold working effect, the overloaded prototype completely masked the true vulnerability of the design, surviving an incredible 16,000 pressurization cycles in testing. But the production aircraft, like the ones lost at Elba and Naples and the one in the water tank, never went through that extreme overpressurization beforehand. Their untreated metal failed at roughly 1290, 900, and 3060 cycles. The very test intended to prove the aircraft's safety had accidentally reinforced the exact areas the engineers most needed to study. Now, we shouldn't exaggerate and say the Comet changed absolutely every single aviation standard in existence, but its legacy is undeniably profound. This grueling forensic investigation served as an enduring lesson. It proved definitively that a test aircraft must accurately reflect the normal production models operating in real service. It vastly advanced the world's understanding of fuselage fatigue, and it paved the way for the transition of early safe life and fail-safe designs into the incredibly rigorous modern damage-tolerant standards that keep us all safe today. Which brings us full circle right back to the modern passenger window. Today, airliner windows are typically oval or rectangular with highly rounded corners. Those gentle curves aren't just there for aesthetics, they allow the massive structural stresses of a pressurized cabin to distribute smoothly around the opening. By eliminating the sharp corners, engineers successfully prevent the severe stress concentration and microscopic fatigue that brought down the early jet pioneers. So, the next time you board an aircraft and look out at the clouds, take a moment to look at the window frame beside you.
Its curved shape reflects decades of hard-won engineering lessons about pressure, fatigue, and the invisible forces acting on an aircraft during every single flight. It's a brilliant solution to a hidden danger. Which makes me wonder, what hidden aviation reason, what unseen part of an airplane should we investigate next? Let us know, and I'll see you in the next explainer.